Okay. Now, now we get the above relation that Q1 is approximately the largest eigenvalue power n times the coefficient. This we can obtain by computing by assuming that is approximately rho of Q is simply the largest eigenvalue, by the way. We simply assume that Q of n is simply rho of n, the spectral radius of n of Q power n times the following. Now, now we know that since that Q1, Q2, Q3 will be a linear combination of the eigenvalues. It will be alpha times the largest eigenvalue 9.5778 plus beta times lambda 2 power n plus gamma times lambda 3 power n. Alpha 1, beta 1, and gamma 1. And the same can be said with alpha 2 and then alpha 3, beta 3, and gamma 3. As n gets large, beta and gamma become less relevant as they approach. If we take 9.5778 power n common, the remaining terms tend to 0 as the function is exponential as a function of n. Therefore, one can assume Q of n as a constant vector times rho of Q power n. This constant vector is nothing but this matrix divided by rho of Q power 100. This matrix will be largely constant as remaining powers of the eigenvalue tend to 0. Now, since we only need to find the matrix recursive relation, and we get the corresponding eigenvalues and the results using the matrix calculator. One can do the same for the king, knight, and the bishop. One simply has to get the relations. Now, king at the corner has 3 different ways to move. King at the edge has 5 different ways, and king at the center has 8 different ways. Now, for the knight, 2 different ways from the corner, 3 different ways from the edge, and 4 different ways from the center. Two at the corners, in the L shape and 2 at the edge. So total 2 at the two in the corner and 2 in the edge. For the bishop, 3 from the corner, 3 from the edge, and 5 from the center. You have 2 additional, which was not present from the corner. So one can find the relations below here. And using the same matrix calculators, we find these eigen values and the results in the same manner as it for the queen. One can confirm this with the matrix calculator. This is for the king, the largest eigenvalue, and the coefficients. For the knight, largest eigenvalue and the coefficients. For the bishop as well, largest eigenvalue, characteristic polynomial, and the coefficients. Now, this is how it's solved for the 4x4 square chessboard for all the 4 pieces. We will cover rook in the end because rook one can solve for any dimension. This we will cover in the end. Now let's get to 8x8, the chessboard. One can also get these 10 equations of these 10 pieces. There are 21 ways from the corner, 25 ways from this layer, 23 from this layer, 25 from this layer, and 27 from this layer. One can get 10 different equations and get a 10 cross 10 matrix for these 10 different squares. Similarly, characteristic polynomial as before can be calculated using the matrix calculator, and so is the coefficients. One can take a look at this matrix for the queen for an 8 cross 8 chessboard with a 10 cross 10 matrix for the equations for the 10 distinct squares. One can find the largest eigenvalue as 22.936 with the coefficients. Now, the same is repeated for the king, the knight, and the bishop, respectively. Now, here comes the tricky part. Now, we have shown the number of ways a queen, a king, a bishop, and a knight can move in an 8 cross 8 board, 4 cross 4 board freely. But we have not fixed any destination. Well, a huge part of the problem relies in a huge part of the problem relies in fixing the destination starting and ending points. Say, how many ways can a queen move from a1 to h8 in n moves? We have covered number of ways a queen can move from a1 to any other square without any ending point. We have we have covered number of ways chess pieces can move with a fixed starting point, but we have not covered for fixed starting points and ending points. Now, for that, we have made certain assumptions. It will still be a constant times the largest eigenvalue, power n. Here P can be queen, king, knight, bishop. So it's simply a constant times the largest eigenvalue of the matrix, power n, will be your answer. The constant can be anything. This is true whether there's a fixed destination or whether there is not a fixed destination. When there's a fixed destination, one can simply multiply probabilities or simply subtract two moves. Since within two moves, any queen can reach any other square. For a king, it may take longer. For a knight as well. So a constant number of moves can be subtracted such that every piece can move freely up till a certain number of moves, say n minus 100, n minus 20, and the remaining 20 moves it can move for the fixed square. So this is one method where the exact constant need not be is not necessary to be found. But if you want to find the accuracy as a percentage, when we have to multiply certain probabilities. So we simply count the squares. There are four yellow squares, four corner squares, and 8 squares from the edges. Every square that is in the diagonal will be repeated 4 times, and every square that is not in the diagonal will be repeated 8 times. So you get this matrix. We assume this matrix as the frequency of each square. And we assume the coefficients as the probabilities of each square. Since the edges are more like, since the center is more likely, it will have higher coefficients, and the remaining squares will have lesser coefficients. So we will leave this one here as an afterthought, since this result is not accurate, and we are using unlikely theories like probability on a combinatorial problem. So this result is not accurate, but this is only an estimate. So we will not cover this for now. Now let's move on to a different piece, the rook. Now the rook is the most interesting of the remaining pieces because it moves in either vertical or horizontal, only one component at a time. It makes the problem easier because we can extend it to any dimension. We will be able to solve for a fixed destination with exact